Hello, welcome to lecture 7 of this course. As you know, in this course, primarily we are going to deal with the interaction of electromagnetic radiation with artificial quantum systems. Mostly the artificial quantum systems, in particular in circuit quantum electrodynamics, they are going to be modeled as two-level atoms. On the other hand, when we are going to deal with quantum optomechanics, the quantum system would be modeled as harmonic oscillator. These electromagnetic radiations, when quantized, they will be also modeled as harmonic oscillator. As we have already learned about two-level atoms, fundamentals of two-level atoms, now let us discuss harmonic oscillators. The harmonic oscillator is one of the most basic model in physics. It describes the dynamics. It describes the dynamics of systems close to the equilibrium state, close to their equilibrium state. Say, consider a potential energy function, say V of x. Let me plot it. Suppose this potential function V as a function of x has a minimum at some position, say x0. Then we can expand this potential function, one-dimensional potential function V of x, into a Taylor series. Taylor expansion would be like this: V of x0 around this minimum equilibrium point, plus here it would be x minus x0 dv of dx evaluated at x is equal to x0 plus 1 by 2 factorial d2v dx2 evaluated at x is equal to x0, and we have x minus x0 whole square, and so on. Now, since x0 is the location of the minimum of the potential energy, its first derivative is obviously going to be 0. So therefore we'll be left out with V of x is equal to V of x0 plus half k x minus x0 square, and there will be other terms as well, where this k is defined as the second order derivative of this potential function evaluated at x is equal to x0, and it's a positive constant. It's a positive constant. Now, since it is only the difference in potential energy that matter physically, we can choose 0 of the potential energy such that V of x0 we can take it to be 0, and if now the position of the origin of our coordinate is at, say, x0, if we shift the origin to the coordinate x0, then we can write V of x is equal to half k x square. Okay, we are taking our coordinate position of the origin of the coordinate at x0 is equal to 0, and if we shift the coordinate origin of the coordinate system to x0, then we can write this potential energy function to be as half kx square, provided the system is undergoing, if the system is undergoing very small or sufficiently small oscillations about the equilibrium point. Okay, so in that case we can neglect all the higher order terms in the Taylor series. Then we can neglect all higher order terms in the Taylor series, and the effective potential energy is that of a harmonic oscillator. So this is the harmonic oscillator potential. In fact, you see, if I write down the equation of motion here for in one dimensional case, so here the force is equal to mass into acceleration, so mass into acceleration x double dot, and that is equal to force is given as dv of dx, right? If we take it, then we are going to get minus kx. So this is what the Newton's second law gives us. In fact, let me use the coordinate q instead of x, and then I can write down the equation of motion like this: mq double dot is equal to minus kq. One typical example of a harmonic oscillator, this is the equation of a harmonic oscillator, and one typical system is of this type. Say a mass of m attached to a spring of spring constant k, so q is the displacement from its equilibrium point, then this is the equation of motion. Alright, here we can also write this equation of motion as q dot plus omega square q is equal to 0, where omega square, as you can see, is simply k by m, and the potential energy function I can write it as v of q is equal to half k q square, or half m omega square q square. And now it looks like, because I have shifted my origin to 0 here, okay, so this is the typical plot of the harmonic oscillator potential energy function. Now we can express this Newton's equation of motion, which is a second order differential equation, in the form of two first order differential equation. If I write, say, q dot is equal to p by m, where p is the momentum, and p dot is equal to minus m omega square q, these two first order differential equations are equivalent to this Newton's equation of motion, q double dot omega square q. In fact, you can very easily get it from this system of first order differential equation. And you see, that means we are actually now going from, when you are in the Newtonian mechanics, we dealt with this variable q and q dot, and when we go over to these two first order differential equations, we are going over to the variable q and p, and this is actually known as going from the configuration space to the so-called phase space. Okay, in fact, this phase space description of classical system is very useful, because we know that as regards quantum mechanics is concerned, in quantum mechanics, these phase space variables q and p, in quantum mechanics they would be represented by operators, and they satisfy this commutation relation qp is equal to I h cross, where q and p are the canonically conjugate variables. As you know, that when we want to discuss the quantum mechanics of a system, generally we look for the Hamiltonian of the system. And in fact, when we go from the classical regime to quantum regime, then we must know the Hamiltonian of the classical system. But to know the Hamiltonian of the classical system, first of all, we need to know the Lagrangian of the system. So in the case of harmonic oscillator also, if we want to discuss the quantum regime of the harmonic oscillator or quantum harmonic oscillator, we first need to know the Hamiltonian of the harmonic oscillator, or even before that we need to know the Lagrangian of the harmonic oscillator. So let us find that out. We know that the Lagrangian of a classical system is given as kinetic energy minus the potential energy, and this, for one dimensional case, it is Lagrangian is a function of the variables q, the position, and the velocity, and this Lagrangian satisfy this so-called Lagrange equation, that is del L del q minus d of dt del L del q dot is equal to 0. So this is known as the Lagrange equation of motion. So in our case, in the case of harmonic oscillator, the Lagrangian would be, for the harmonic oscillator, for the classical harmonic oscillator, the one-dimensional classical harmonic oscillator, the Lagrangian would be half m q dot square minus half m omega square q square. So this is the potential energy part, this is the kinetic energy part, and it satisfies this Lagrange equation of motion, which is nothing but the so-called Newton's equation of motion. That is what we are going to get. You see, you have del L del Q is equal to, you will get from here, it will be minus m omega square q, and del L del Q dot is equal to m q dot. Okay, and in fact del L del Q dot, this quantity is known as the conjugate momentum of the harmonic oscillator. Okay, mass times velocity, or I can write q dot is equal to p by m. So if I put del L del Q and this quantity in the Lagrange equation here, then you see from the Lagrange equation I will get minus m omega square q minus mq double dot is equal to 0, and which is nothing but q double dot plus omega square q is equal to 0. So we rederive the so-called Newton's equation of motion for the one-dimensional harmonic oscillator. Alright, now coming to the Hamiltonian of the harmonic oscillator. For one-dimensional case, the Hamiltonian of a classical system is given by this one, q dot p minus the Lagrangian. So in the case of the harmonic oscillator, the Hamiltonian would be, you see, this Hamiltonian is a function of position and the momentum variable. So therefore I have to express everything in terms of position and momentum only, q and p variables. So I need to get rid of this q dot. So okay, so here I know that q dot I can write it as p by m. So I have here p by m and then p from here. Then the Lagrangian is half m q dot square minus half m omega square q square. But again I have to replace this q dot by p by m square. So if I do the maths, so it is very easy to see that I am going to get this familiar form of the Hamiltonian for one-dimensional harmonic oscillator, p square by twice m half m omega square q square. So this Hamiltonian, we are now expressing it in terms of this variable q and p. This Hamiltonian satisfy the so-called Hamilton's equation of motion, and these variables q and p are called canonically conjugate variables, and they are called canonically conjugate variables. Actually, any pair of variables are called canonically conjugate variables if they satisfy the so-called Hamilton's canonical equation of motions. So, or simply called Hamilton's equation of motion. So Hamilton's equation of motions are, one equation is q dot is equal to del h del p, and another equation is p dot is equal to minus del h del q. In fact, you can verify that indeed this q dot, and in fact let me quickly see for the harmonic oscillator case. For the harmonic oscillator case, we know the Hamiltonian, so del h del p. From here you see that this is going to give us the familiar equation p by m. So this already we know that this is correct, and here p dot, if I take del h del q from here, then you will see I will get this force equation here, that is m omega square q. So this is also, we know that this is Newton's equation. These are the correct equations, correct form of equations. So these variables q and p they satisfy the so-called Hamilton's equation of motions, and that's why they are called canonically conjugate variables. And apart from that, another thing is that these canonically conjugate variables Q and P, they satisfy the so-called Poisson bracket. This Poisson bracket is equation is satisfied, and let me just remind you that the Poisson bracket between two classical quantity AB is defined like this. It is del A del Q del B del P minus you will have del B del Q del A del P, and you can easily verify that QP is equal to 1. And now, knowing all these things, we can easily go from the so-called classical to quantum harmonic oscillator, and this transition is very simple. And this quantum harmonic oscillator we can go, and this transition is known as the canonical quantization. The only thing that we have to do, that these variables, canonically conjugate variable Q and P, they are now going to be replaced by their corresponding operators in quantum mechanics, and these Poisson brackets QP, these Poisson brackets are going to be replaced by the so-called commutation relations for the corresponding operators between the variables Q and P. So in QP, we know that that is equal to IS cross, and this Hamiltonian now would be written in terms of these operators. So H is equal to P square by 2 M. Here P is now the operator, and I have half M omega square Q square. So thereby we basically obtain the so-called Hamiltonian for the quantum harmonic oscillator. Quantum mechanical Hamiltonian can be obtained. So the procedure is very easy. Let me just once again tell that in any classical system, this way we can hopefully quantize it, provided first of all we need to know the Lagrangian of the system. It may have only in one dimension. This is what we can do, extend this argument for any dimensions. So first thing is that we need to know the Lagrangian, then we need to find out the Hamiltonian, then we need to this Lagrangian would be function of Q and Q dot, then we need to find out the Hamiltonian, and once we find that the Hamiltonian, we have to check whether these variables, basically we need to dig out the canonically conjugate variable, because these conjugate variables are going to satisfy this Hamilton's canonical equation of motion. So that's what we have to do, and if we can do that, if we can find out this canonically conjugate variables, then we'll also see that they satisfy the so-called Poisson bracket relation. And if we have all these things with us, then the next step is just to find out replace it by the corresponding operators, and they will satisfy this uncertainty relation, this commutation relation, and the corresponding operator H, everything would be replaced by this operator. And this is the procedure, and this is the general procedure that we are going to apply for any classical system. Later on we'll see in our course that we are going to quantize the so-called LC circuit. There also this would be the kind of procedure that we are going to adopt. Now from your elementary quantum mechanics course, you may know that the Hamiltonian of a harmonic oscillator satisfies this eigenvalue equation, where psi n is the energy eigenstate and En is the energy eigenvalue, and En is given as n plus half h cross omega. H cross is the so-called reduced Planck's constant, defined as h divided by 2 pi, and you know that h is equal to 6.626 into 10 to the power minus 34 joule second, and omega is the angular frequency of the harmonic oscillator, and n takes integer value 0, 1, 2, 3 like this. And one thing that you can immediately see is that energy levels in a harmonic oscillators are equally spaced. Say you have n is equal to 0, n is equal to 1, n is equal to 2, and so on, and the spacing between these energy levels are always equal, and that is h cross omega. In fact, this is a unique one of the unique characteristics of harmonic oscillator, which sets it apart from other quantum systems. And by the way, this integer n here, n in this energy eigenvalue expression uh, refers to the number of quanta. So n refers to the number of quanta, and this quanta has different name in different situations. For example, it is called phonons. These quantas are called phonons when we discuss vibrations in vibration in solids, or a mechanical oscillator. If we model a mechanical oscillator as an harmonic oscillator, then these quantas would be called phonons. On the other hand, if we talk about electromagnetic fields or light, these quantas are called photons. So for electromagnetic field or light, these quantas are known as photons. Okay. Now, instead of psi n, actually most of the time we can write it by this kate n here, and in that case our energy eigenvalue equation would become like this. So here n is also known as Fock state, or it's also called number state. And this kate n, or this Fock state here, it's basically refers to the state. It refers to the state where there is n number of quanta. Okay. Now there is a very useful formalism called operator formalism of harmonic oscillator, and which is going to be very useful for us. The idea here is that we can introduce operators which may take us from one energy state to another energy state. Say if we introduce operators where we can go from, say, this ground state to the these operators may take us from the ground state to the excited state, or we may go from the excited state to one another lower state, and so on. So these operators are called creation and annihilation operators. Say we want to go from from the energy state n to n minus 1, okay, lower energy state. Then we have to operate it by an operator that is called the annihilation operator. You are going from a energy state n to n minus 1, and this is what you will achieve by this annihilation operator, and maybe some of you already know. And then there is a creation operator where it is going to take us from n to n plus 1, and this prefactor here would be square root of n plus 1. And these operators are defined such that when you operate on the ground state, because there is no energy state below this ground one, so you have to get 0. It is going to be defined in that way. And also a and this is annihilation operator, and the creation operator satisfies this commutation relation, that a dagger has to be equal to 1. Further, what turns out that a dagger a, this bilinear combination, when it operates on this energy eigenstate or Fock state n, then it's going to give you a number and this operator is symbolized as this n cap, and this is called the number operator a dagger a. So I am sure most of you know all these things, but I'm just recapitulating and reminding you. All right. Now, in terms of this creation and annihilation operator, this our original harmonic oscillator Hamiltonian p square by twice m plus half m omega square q square can be expressed in terms of annihilation and creation operator in this useful form h cross omega a dagger a plus half. Okay, in fact, uh, these all these things that I have written here would be satisfied if we define this annihilation and creation operator this way. Say this position operator is written as a combination of, say, a plus a dagger, and this is dimensionless and it has to be multiplied by a dimensional quantity, say q0, which has the dimension of length. In fact, q0 refers to, this as the dimension of length, refers to the spatial width of the ground state wave function. It refers to the ground state wave function of a harmonic oscillator, of the harmonic oscillator. What I mean by that is that you know that the ground state, for the ground state from your elementary quantum mechanics, you know the ground state wave function of the harmonic oscillator is Gaussian, and if you calculate the width of this Gaussian in the ground state, you are going to get q0. So if you can say the width is del q, if you work it out, you are going to q0. What I mean to say is that you have to just calculate the standard deviation, or first you calculate the variance, and variance in the ground state with respect to the ground state, if you calculate, that is your q square 0, okay, minus 0 q 0 whole square. And if you want to find out the width, you just have to take the square root, and if you take the square root, you are going to get simply q0. And in fact, it would turn out that this guy is nothing but h cross. If you do the calculation, this would be h cross by twice m omega. Okay, and so therefore what we have basically is that this position operator is now defined in terms of the annihilation and creation operator like this, and the corresponding momentum operator is defined as, by definition, it is I m omega q0 a dagger minus a. In fact, you can write from these two equations, you can write annihilation and creation operator like this. Annihilation operator would be 1 by 2 keys q0. You will have q plus ip by m omega, and a dagger is basically the Hermitian conjugate of this annihilation operator. This is the creation operator, that would be 1 by twice q0 q minus I p by m omega. So these are extremely useful relations, and you should remember it all the time. Now let me briefly talk about the thermal equilibrium statistics of a harmonic oscillator. You know that photons or phonons, these are bosons, and when a harmonic oscillator is in equilibrium with its environment at some temperature, say T, Bose-Einstein statistics basically determine the occupation probability of each energy level, and this is given by occupation probability of an energy level in a harmonic oscillator is given by this expression. So this is h cross n h cross omega by kBt, or 1 minus exponential minus h cross omega kBt I hope you have get this expression or learned this expression in your statistical physics course. Actually, let me quickly show you how this expression can be obtained very easily. If you can start from the very basic statistical mechanics, because you know that if I as per this Gibbs canonical ensemble or distributions, Gibbs canonical distribution, Gibbs canonical distribution, you know that the occupation probability is dependent on is given by this expression. This is proportional to e to the power minus, say, energy divided by kBt. Kb is the Boltzmann constant, T is the temperature, and for harmonic oscillator, okay, for En, and for harmonic oscillator, obviously you have it would be n plus half h cross omega by kBt, okay, kBt. And I can actually, this half h cross omega is a constant term, so I can take it into this constant. I can write it again, include it in the constant c. Then I have e to the power minus n h cross omega by kBt. So this is my starting expression, and I know that the total probability has to be equal to 1, and from here you can easily find out this constant c. If you take it out, c, and this is a, you will get a series actually. kBt is equal to 1, n goes from 0 to infinity, and this I can now write it as 1 plus e to the power h cross omega by kBt plus e to the power twice h cross omega by kBt, and so on, and it is 1. So this one is 1 divided by e to the power h cross omega by kBt. Okay, so you get the constant from here, that is simply 1 minus e to the power h cross omega by kBt. And so you see, you finally got these expressions here. Okay, let me just complete it. So you will get Pn is equal to this constant 1 minus e to the power h cross omega by kBt. That is what you have, this one, and then e to the power minus n h cross omega by kBt. So that's how you get the expression finally. You can, if you can just rearrange, okay, you get it actually. This is, I can now take it this side, and then you will get what I have written originally. Now I hope all of you, by the way, know that this Boltzmann constant kb, it's useful to remember, that has a value 1.38 into 10 to the power minus 23 joule per Kelvin. Now using this, I can easily find out the mean occupancy, of the oscillator, of the harmonic oscillator. That is, I can just have to find out the average number of quanta, and we just have to calculate the expectation value of this number operator, or I can just calculate this quantity n into the probability Pn. And if you, I'm just leaving it as an exercise to you, you can very quickly do it. You know, Pn expression is already, it is there with you. You just have to expand it. Then please show that the expression that you are going to get is 1 divided by h cross e to the power h cross omega by kBt minus 1. And this is a very useful expression, and this is one of the quantity which is by which I can actually tell whether a system is quantum or not, to characterize the system. For example, in the classical limit, in the classical limit, your this quantity kbt is much greater than h cross omega. What I mean by that is, in the context of harmonic oscillator, that means this harmonic oscillator is going to behave classically because the energy spacing, the thermal energy, would be much larger than the energy spacing between two energy levels. Okay, so the whole system will actually behave like, you will not be able to see this discrete nature actually. So in that case, this harmonic oscillator is going to behave classically, and in the classical limit, if you look at from this expression, then you will get this average number of quanta would turn out to be, when kbt is much greater than h cross omega, you can easily see that that would be kbt divided by h cross omega. So in a to give some examples, say in a typical micro or nanomechanical oscillators, where this resonance frequency or this frequency omega is basically in the range of 1 to say 1 megahertz to say 1 gigahertz. 1 megahertz means say 10 to the power 6 hertz, and 1 gigahertz refers to 10 to the power 9 hertz. So this is for a typical nanomechanical oscillator, nanomechanical or say micromechanical oscillators. So this is the frequency, the resonance frequency. Then if you put the numbers, suppose at room temperature T is equal to 300 Kelvin, then you will find that the mean number of quanta would turn out to be, if you put Kb, if you put T is equal to 300 Kelvin, okay, so on, then you will find that that would be around 10 to the power 4. The mean number of quanta would be 10, this much. So which is a very huge number, and that's why you cannot observe the quantum behavior of this kind of oscillators at say room temperatures, right? To see the quantumness of this, because of this quantity is very high, so you have to, if you can reduce this number, and that you can do provided you do some kind of cooling. Okay, you have to cool these oscillators, and then only you will be able to see the quantum behavior. In fact, in this context, let me talk about, there's another kind of oscillators that we are going to encounter, and that is the so-called electromagnetic oscillators or electromagnetic fields. And electromagnetic oscillators or light, basically this has typical frequency of light, if I can consider them as some kind of oscillator, and they have a frequency on the order of 10 to the power 14 hertz. And if even it at room temperature, if you try to calculate their mean occupation number of the quanta, or basically mean number of photons at 300 Kelvin, then just use this expression. If you use this expression, you know all the parameters, then it would turn out to be around 10 to the power minus 35, which is a you see, that means it's a very small quantity. It's nearly zero. So that's the reason that optical fields, this is refers to optical fields or fields. So optical fields at room temperature, optical fields at room temperature can be, because this is nearly equal to zero, can be safely considered to be in their ground state, Okay, and this issue is going to be very useful. Why I'm saying that? Because if you have a mechanical oscillator, say you have a oscillator like this, and if you make it, in contact with an optical field, suppose you have an optical field, even if it is at room temperature, the optical field is, or at some finite temperature, you can consider it to be at temperature T is equal to 0 because it is in the ground state, and this mechanical oscillator, this is the mechanical oscillator, this is at some finite temperature, optical field at 0 temperature. So therefore if you keep the mechanical oscillator with this optical oscillator or optical field, and then thereby you can get you can actually cool the mechanical oscillator. This is actually very elementary way I can explain cooling of a mechanical oscillator. Now one useful information that we'll require later in this course is the evolution of this annihilation operator. Evolution of A annihilation operator. This can be easily found out by using the so-called Heisenberg equation of motion, which we learned in the last class. Annihilation operator satisfies this Heisenberg equation. Here H is the, let us work it out. H is the harmonic oscillator Hamiltonian. So A H cross omega A dagger A plus half. This H cross omega half is a constant term, so that's not going to contribute. So we can now write this as H cross omega A dagger A, which we can further write it as S cross omega A dagger A, and you know that commutation relation between A and A dagger is equal to 1, so we'll have H cross omega A. So that means we get this simple differential equation, and the solution of this differential equation is trivial, and you can easily see that the solution will be A of t is equal to A of 0 e to the power minus I omega t. So this is a very useful relation, and we are going to encounter it many times later on. In fact, I can depict the evolution of this annihilation operator in a picture. Just remember that A, as per our definition, this is the 1 by twice q0 q plus I p by m omega. So the real part of this annihilation operator is associated with position, and the imaginary part of the annihilation operator is associated with momentum. And taking this as the hint, what I can do, I can plot it. If I take my x-axis as the real part of any, sorry, I cannot actually plot an operator. What I have to do, I have to take the expectation value of the operator. If I take the expectation value of the operator, annihilation operator, the real part would be, you can see from this expression, that would be simply expectation value of q position operator divided by twice q0. So this has a dimensionless, so we can term it as normalized position. So x-axis is our normalized position. On the other hand, the y-axis is imaginary part of A annihilation operator, and which you can see from here, that would be the expectation value of the momentum operator divided by twice m omega q0, which has the dimension of momentum. So this is again normalized momentum. Okay, now all right, now to plot it, because of the fact that here we have, right, A of t, if you look at this expression, it is very clear that the magnitude of A of t remains constant, magnitude of A of t, because of this exponential factor. So this remains constant in time. Okay, so only it is multiplied by this phase factor here, and phase varies linearly in time. The phase phase factor, if you look at it, it is the phase factor is e to the power minus I omega t, and this phase varies linearly in time, and it rotates here. Actually, because of this minus sign, this rotates in the anti-clockwise direction. It rotates in the anti-clockwise direction, and evolution basically takes place. This is say minus omega t at time t, and this evolution is happening in a circle because the magnitude is constant. As a final topic of this particular lecture, let us discuss how to model a system of coupled harmonic oscillator quantum mechanically. So say we have a two spring mass system like this. I have a spring of spring constant K01 and mass M1 is attached to it, and another spring or spring constant K02 and a mass having M2 is attached to it, and they are coupled by a spring of spring constant K. Say this mass oscillator is also displaced from the equilibrium position by x1, and then this is displaced by x2. Then you know that the Hamiltonian of this whole system, this coupled system, would be as follows. So you'll have p1 square by twice m1 plus half k01 x1 square. This is the energy of the first oscillator. Then for the second oscillator, you will have p2 square by twice m2 plus half k02 x2 square. That is the energy of the second oscillator if that is not coupled. These are the individual energies of the oscillators when they are not coupled, but because of coupling they would have another term that would be the coupling energy between them, that is a half k x1 minus x2 square. So this term is very important, so let me analyze it little bit further. So this coupling term or coupling energy term for the two oscillators, that is half k x1 minus x2 square. If I open it up, then I will get half k x1 square plus half k x2 square minus k x1 x2. Now if you look at these terms, this term and this term, as such, qualitatively speaking, it is not going to change the physics of this coupled system, because these two terms are actually changing the spring constant of the individual oscillators, but interesting term is this cross term, which is actually refers to the fact that energy is getting transferred from oscillator 1 to oscillator 2. So let us analyze this particular term. So this term here, if I now want to study quantum mechanics, if I go to the quantum regime, then I can write x1 and x2 in terms of creation and annihilation operator. So let me do that. So you will have x1 would be, you will have, as per our definition, it would be say q01 a1 plus a1 dagger. Just to remind you that we defined earlier that this position operator we can define as q0 a plus a dagger, right? And therefore here I have x1 would be represented by this one, and x2 would be again q0 2 a2 plus a2 dagger, and here q01 is h cross divided by twice m omega 1. So that is for the first oscillator, this is the 0-point fluctuation, and q02 is h cross divided by twice m 2 omega 2, it will be m1 here. So this is what we have. Now if I open it up, then I can actually rewrite it like this: k q01 q02, and I will have a1 plus a1 dagger and a2 plus a2 dagger. So this is what I will have. And if I talk about the uh, quantum mechanical version of this part of the Hamiltonian, then I will have, it would be represented by, say, h cross omega 1 a1 dagger plus a1 plus half, and similarly here this part would be h cross omega 2 a2 dagger plus a2 dagger plus half. We are going to neglect these two terms because they are just basically changing the spring constant of the individual springs. So therefore the total quantum mechanical Hamiltonian for this classical system, if we go to the quantum regime, then the quantum Hamiltonian would be h cross omega 1 a1 dagger plus a1 plus half term is there, but let me ignore that because that's a constant term. And similarly for the second oscillator I will have a2 dagger a2, and we have this coupling term here, that is that I have as minus k q01 q02 a1 plus a1 dagger plus a2 dagger. These are operators. Okay, but this one, let me write it in a, because this has the dimension of energy, so let me write it as h cross z. Z is the coupling coefficient between the two oscillators. So finally the quantum mechanical Hamiltonian I can write in this particular form. That would be for the second oscillator I have this one, and when they are coupled, this is the coupling part of this two oscillator, a1 plus a1 dagger and a2 plus a2 dagger. Okay, now let me analyze a little bit further this particular coupling term. If I look at this coupling term, you will see that I have, okay, just let me take the product here, that is a1 plus a1 dagger and a2 plus a2 dagger. If I open it up, then I will have four terms. That would be a1 a2 a1 a2 dagger plus a1 dagger a2, and I will have a1 dagger a2 dagger. All right. Okay, so what these terms physically mean, if I look at these two terms, so a1 a2 dagger, this basically means that in an excitation is getting destroyed in oscillator 1, and that is and one excitation is created in the oscillator 2. Okay, so and similarly, okay, let me write here excitation. Here it means that excitation is destroyed in oscillator 1, and excitation is created in oscillator 2. So basically now from oscillator 1 to oscillator 1, excitation is getting transferred. On the other hand, the other term, that is a1 dagger a2, here the opposite things happen. Excitation is now destroyed in 2 and it is transferred to 1. So these two terms are called resonant term, and because of the fact that we already know that how a1, this annihilation operator or the creation operator, evolves in time. If you look at it, a1 evolves like in time, it will evolve like e to the power minus I omega 1 t, and the other one will, it is because it is a dagger, that will be plus I omega 2 t. So overall this whole combination would evolve as I minus I omega 1 minus omega 2 t. Now if omega 1 is nearly equal to omega 2, you see that basically refers to the fact that we had energy h cross omega 1 in oscillator 1, and that is getting transferred to oscillator 2, which is having energy h cross omega 2, which is, if omega 2 is nearly equal to omega 1, then that is quite physical, means simply energy is getting transferred from one oscillator to the other oscillator, and that's why they are called resonant term. On the other hand, if you look at these two terms, A1 dagger and A2 dagger, sorry, this would be A1 dagger, A2 dagger. If you look at this term, this implies this A1 and A2. This means that excitation is destroyed in oscillator 1 and excitation is destroyed in oscillator 2 as well. So simultaneously excitation is destroyed in the two oscillators, or okay, let me write here, that is simultaneous destruction of actually quanta or excitations in oscillators, in both the oscillators, or opposite things is happening at, that is simultaneous creation of excitations in, I can just let me just copy it here. So the same thing I can, instead of this one, I have simultaneous creation of excitation in oscillators. Okay, so actually these two events are very unlikely, and it is not physical also. Initially you had nothing and now you have destructed or created two excitations, so this is not physical, and this can be actually neglected. These two terms can be neglected. These two terms can be neglected on physical ground. In another way to look at it, these are actually called non-resonant terms. So if you again look at the time evolution of these two operators or these two combinations, you will see that this one A1 and A2, they would this it would be e to the power I omega 1 plus omega 2. Okay, and similarly for the other one, A1 dagger, A2 dagger, this in the time evolution will go like this, omega 1 plus omega 2. That's why these are called non-resonant terms. They are called non-resonant terms and they can be neglected. If and when you neglect this is actually another form of the so-called RWA, or the rotating wave approximation that we discussed earlier. So under RWA, this Hamiltonian, finally I can write for the coupled oscillators, it would be h cross omega 1 A1 dagger A1 plus h cross omega 2 A2 dagger A2, and we have this coupling term h cross z A1 dagger A2 plus A1 A2 dagger. Let me stop for today. In this lecture, we have learned about the fundamentals of harmonic oscillators. In the next lecture, we are going to see how to quantize electromagnetic radiations. It turns out that when quantized, electromagnetic radiation behave like a infinite collection of harmonic oscillators, and the quanta of these harmonic oscillators are known as photons. So see you in the next lecture. Thank you.